Okay, now we got to progress to the AP level of analyzing 2D motion, so a little more general, a little more complicated, because you are ready for it. So in general, we can consider a particle moving along a curved path from P initially to Q later on. And so the initial position is just specified as the vector R0. Okay, in this case it's two-dimensional. Then we have a change in that position equal to delta R from P to Q, giving us a final position, R, realizing that these R values have X and Y components, right? So now we have R with an angle theta. Okay, so R0 plus delta R is R, and each vector, as I said, has those I and J components, X and Y. So we have X in the I, we have Y in the J. That's specifying the position. So combining this, we have the position R is really XI plus YJ in unit vector notation. Magnitude of R, square root of the sum of the squares, x squared plus y squared. And the angle is inverse tangent of y over x. All that's familiar. The average velocity, delta R, over delta t. So it's literally just this, the size of this thing, divided by the time it takes to go from here to here. So that's the average velocity. Now here's the initial velocity at P, and here is the final velocity at Q. All right, so there's specific velocities along the way, of course, which is the limit as the delta t approaches 0 of delta R over delta t. So that's just really the derivative of the position at any point, dr dt. Okay, so we're talking about the generalized velocity, dr dt, which is the derivative of xi plus yj. And you treat them separately. So that's dx dt plus dy dt j. Derivative of x with respect to time, I. So it's basically the horizontal and the vertical components of the velocity, vxi plus vyj. Likewise, consistent with this, the magnitude of v, and this two-dimensional, square root of the sum of the squares, and the angle of the velocity is inverse tangent of vy over vx. So we can extend this to acceleration, the second derivative of x, I, plus the second derivative of y with respect to time, j, axi plus ayj. Magnitude of a, square root of the sum of the squares, the angle, the direction of the acceleration, at any point, inverse tangent of ay over ax. Also we have that v is equal to integral of acceleration. The position is integral of the velocity, usually involving components, I, j, and perhaps even k. Okay, some AP projectile motion. We have y as a function of x. So there it is. We have v0 at an angle. Should call it theta 0, I suppose. We have vx0 and vy0, producing the v0, right? So the position in the x direction, vx0t. Therefore, the time is the position in the x over the velocity in the x. So we're going to use that to sub in a moment. So the vertical position equation, y0 plus vy0t minus 1/2 gt squared. But now, of course, this is with respect to time. We'll assume y0 is 0 in this case. So we're starting and ending at the same elevation. Important point here. Let's sub in this for time and rewrite the equation. So we have y equals vy0 times time minus 1/2 g time squared. There it is. Now what does that give us? Y is vy0 over vx0 x minus 1/2 g over vx0 squared x squared, which is equal to bx minus ax squared. Well, this is the form of a parabola, the equation for a parabola. More specifically, what is vy0 over vx0 but tangent of theta. Tangent of theta 0 at least. So y is tangent theta 0, x, minus g over 2, vx0 is v0 cosine of theta. Quantity squared, x squared, and that's your projectile motion equation. That's quite general. Do you have to memorize that? Probably not, but you should be familiar with its derivation. Maximum height of a projectile, take 2. Here's y max. You're familiar with that. Vy is equal to 0. Vy is equal to v0 sine of theta 0 minus gt. Gt up, the time to get to the top of the flight. So Vy 0 minus gt. All right. From this we can solve for time. Time is v0 sine of theta 0 over g. We're going to use that to sub in the equation for height. Y max in this case, which is no initial height. Initial velocity v0 sine of theta 0 in the vertical direction times time. We just solved for and are now subbing in. Minus 1/2 g times squared. And this gives us v0 squared sine squared of theta 0 g minus, well, v0 squared sine of theta 0 squared times g over 2g squared. Anyway, we have some cancellation here. And when you work this out, you get height, maximum height, is v0 squared sine of theta 0 squared over 2g. Now, do you need to memorize this? Once again, no. You can solve it with the older familiar ways. But here is a nice expression for the maximum height that's already used time as a substitution to get right to the point. And now a more advanced formula for the range of a projectile. Likely you've seen this in your first year of physics. So here is a projectile starting and ending at the same position, which is going to be 0. Y is equal to 0. So we need the time of the entire flight from y is equal to 0 to y is equal to 0. Then we'll plug into the basic range equation, which is how fast it's going in the x direction, which is this, times that total time. Well, y is 0, which is equal to vy0t, or v0 sine of theta 0t, the entire flight time, minus the additional distance from gravity, which is reducing that initial velocity distance. So this is fighting against this, all right? So minus 1/2 g total flight time squared. So we can solve for the time from this, and we get 2v0 sine of theta 0 over g. Now the range is v0 cosine of theta. The vx is all that is, times the time. So just combine this together, 2v0 squared cosine of theta sine of theta over g, and the double angle formula, or half angle formula, I guess it's double angle formula. Range v0 squared sine of 2 theta 0 over g. What's the maximum r? The maximum r is going to occur when this range is maximum. It is going to be maximum when sine of 2 theta 0 equals 1. That's going to happen when 2 sine of theta 0 equals 90 degrees, or the maximum angle, the maximum displacement, the maximum range is when the angle is 45 degrees. How about another way to solve for centripetal acceleration? We already considered rotating vectors at a previous point. We had circular motion speed 2 pi r over t, centripetal acceleration 2 pi v over t, because of the correspondence, the tight analogy between these quantities, revealing, yielding, manifesting. Centripetal acceleration is v squared over r. Now let's consider a circle, radius r, and we have perpendicular to that a displacement, which is circular speed times time, a little delta t. All right, so a tiny amount of time later, we've got a new r and a h, if you look at this triangle. All right, so we have that additional h. Now we have an acceleration, inward acceleration. we're going to try and solve for. That corresponds to, in the amount of time delta t, that acceleration has to be sufficient to reduce this to this arc path here. So it has to traverse this distance in delta t with acceleration a. Now, height is 1/2 at squared. When we have this right triangle, so we have r plus h squared, Pythagorean theorem here, is r squared plus d squared. Expanding that, all right, r squareds go away. Now in the limit, as t approaches 0, h gets really small, h squared approaches 0. So in the limit, we can eliminate the h squared, and we have 2rh equals d squared. And 2r times h, well, you know what h is, it's 1/2 at squared. Stick that in here. Equals d squared. D is vc delta t. And rat, I can't say rat squared, but rat squared, equals v squared t squared. And finally, centripetal acceleration is v squared over r. Consider yourself duly enlightened. Let's briefly consider vertical circular motion that's not uniform. So here's a circle defining the path of, say, a body moving around. Say it's the stopper of physics swinging around under a gravitational field, perhaps that exists underneath here, and that is going to affect the vertical motion of the object. So up at the top we have velocity v1. Of course, you know it's always tangent to the circle. As it's rotating counterclockwise here, over here it's sped up a little bit, so this is a little bit larger of a vector, v2. v3 is the largest because it's at the bottom, and then v4 is some intermediate value on its way back up. So let's specify here the acceleration at position 1. It's all perpendicular, which is straight down. That's pretty simple. Over on the side here we have the perpendicular part of the acceleration, but that's not the whole story. Down here at the bottom we have the full acceleration is perpendicular, and here's the perpendicular acceleration. So I've shown all the perpendicular accelerations, but it's not only that. Okay, the perpendicular is the radial acceleration. That's the radial component. So a radial, v squared over r, that's the size of that acceleration. Not constant because the speed is changing at various locations. So over here on the side we have a parallel acceleration, parallel to the motion, obviously speeding it up. So that's added to the perpendicular. Combining those two, we get a total acceleration a2 in the red. The red is the combined acceleration. Here at the top, that's all there is perpendicular. The bottom, the same thing. Acceleration at position 4, we also have a parallel component, actually anti-parallel, slowing it down. So when you combine these two accelerations, we get acceleration 4 at some intermediate angle, so to speak. So we can express that tangential acceleration equated to the parallel. It's tangential. And it's the rate at which the magnitude of the velocity is changing. So the tangential acceleration is d magnitude of v dt, the rate, the time rate of change of the magnitude of the velocity. Get it? So we can fully express the acceleration now. We've got to put two parts to it, namely the v squared over our radial component, and that's a vector. And we add to that the time rate of change of the magnitude of the velocity, or the speed. And that is the fully expressed acceleration. And that's a pretty interesting looking animal, isn't it? So a little consideration of general curved motion, y versus x. Here is our generalized path and a generalized point on this generalized path that's moving along the path. Now at this point, nothing is given about its motion. But there's its position, its two-dimensional position with I and j components, and now something is known about its motion. Actually, we already knew it had to be going either in that direction or the exact opposite direction. Why? Because the velocity is always tangent to the path. Right? It's always got to be tangent to the path. What about the acceleration? Oh, I just made a choice. You didn't know it looked like that. Now you do. Now there are limits to what the acceleration can be. The acceleration has to exist on the top half of a tangent line here, in the inside curve, not underneath the tangent at that point. So on the upside of that tangent, it can have potentially any direction you might want. So it can have two components. First, we can have a tangential component, and in this case it does. You can visually see that it does. Now the tangential component is the rate at which the speed changes. So there it is. So here's the speed, and this is a vector corresponding to the rate at which that speed is changing. In this case, it's diminishing. It's getting less, slowing it down. All right. In addition to that, we can have a radial acceleration. It's just our familiar v squared over r. So if you consider the motion of this particle, here's the acceleration. The radial part then is simply that. So it's perpendicular to the tangential acceleration, the two perpendicular acceleration components. So putting that together, the magnitude of the acceleration is magnitude of the derivative of the velocity with respect to time. So the rate at which the velocity changes, the magnitude of the rate at which the velocity changes equals this acceleration vector magnitude. Okay, that's kind of interesting. That's the magnitude of the acceleration vector. Notice that these two things are not the same. dv/dt is not dv/dt. Well, the derivative of the magnitude of the velocity, the rate at which speed changes, is this one. This is the magnitude of the rate at which the velocity is changing. So the velocity changes. There's a total velocity change. The rate at which that happens has a certain magnitude. That magnitude is expressed by the size of this acceleration vector. There you go. Some interesting curved motion concepts. And finally, another stab at relative motion. Keep in mind that in any relative motion, the frame of reference is very important. We have a stegosaurus, and we have a tyrannosaurus, a velociraptor, and a lizard. Can't forget the pterodactyl with the fish in his mouth. Bet you didn't know dinosaurs sounded that way, did you? All right, we're going to find these variables: V, velociraptor; T, tyrannosaurus; S, stegosaurus; L, lizard. And now we want to find the position of the stegosaurus from the point of view of the lizard. RSL. Well, that'll be RST, the stegosaurus position from the point of view of the tyrannosaurus. That's this. Plus the position of the tyrannosaurus from the point of view of the velociraptor, or with respect to the velociraptor. That's that one. Position of, plus position of the velociraptor with respect to the lizard. So adding those vectors, we get this resulting vector, which is the position of the stegosaurus with respect to the lizard. Now, we can take the rate at which those positions change. There's a direct correspondence with all these. The rate at which the position of the stegosaurus changes with respect to the lizard is the rate at which RST changes, plus the same thing for TV, same thing for VL. So, these are velocities. The velocity of the stegosaurus with respect to the lizard. Well, we have to put these velocities. I'll add the velocities here. This is the stegosaurus velocity, tyrannosaurus velocity, velociraptor, and lizard. All right, so what is the velocity of the stegosaurus from the point of view of the lizard? Well, we have to add all the velocities up, which essentially is what this is doing here. So VST plus VTV plus VL. And there it is. Now we could physically do that with the vectors, and it would be no problem at all. Just keep everything straight. Notice the outer subscripts on what you're looking for has to match the rest of the vector equations. So there's basically the inner and outer subscripts match, and the T and the V here are like placeholders to make it all work. That'll conclude our basic introduction to two-dimensional and three-dimensional, I guess, motion for AP Physics.